Last time we did many examples which are used in computer science related to probability. So very basic questions like how do you sample a number from a range 0 to m minus 1, okay, where m can be anything. So then you saw that we basically reduce it to log m coin tosses, and we keep tossing until we get a number in this range 0 to m minus 1 and not m or more. And we saw that this actually is a very fast algorithm. You only need to toss 2 log m coins, or the same coin 2 log m times. That is the expectation. We did this by the geometric distribution. So the lesson you learned here is that expected number of steps here came out to be 1 over the probability, reciprocal of the probability, which is 2 raised to k by m. And then using this we can actually also sample a subset of size k. Okay, so subset means that you want distinct numbers from the set S. So this was quite similar, and we saw that first 2 elements that it gives you, T1, T2. So the probability of getting T1 comma T2 where T1, T2 are different, this comes out to be 1 over m choose 2. Okay, so which means that amongst all possibilities, this is all the possibilities have the same probability of turning up. Okay, so similarly you can get that probability of S being a subset or the subset T1 to Tk. Okay, this probability is really 1 over m choose k. Okay, so which is really uniform probability over all the k subsets. And then of course you are interested in the number of times this go-to happens, right? This mistake happens. So this seems to be an infinite loop again. So when is this infinite loop, seemingly infinite loop, going to stop? What is the expectation of the number of attempts? So that will come out to be, so expected number of iterations in this for loop for an I. So that comes out to be again like the geometric distribution we did last time. It is 1 over the probability, so it comes out to be m over m minus I plus 1. Okay, at the ith step, I minus 1 have been picked, elements have been picked. So you want m minus I plus 1 possibilities. So that over m is the chance of correct x. So it is this, and then you sum it up over all I. So this means that expected number of steps in the algo is sigma I 1 to k and m over m minus I plus 1, right. So which is m comes out, you have 1 over m plus 1 over m minus 1 plus 1 over m minus k plus 1. So what is this sum? If k is very close to m, then this is really the harmonic series. Okay, so this is actually equal to m times log m for large k. Otherwise it is different. Otherwise, when if the k is very small, then this is like 1 over m, so you get constant. Okay, so for small k, this is like k steps in the algorithm, which is similar to picking one element. But if you are picking many elements, so k is large, then it comes out to be m times log m. But either way, it's quite small. Okay, so where are we now? So you have learned how to sample one element, k elements, and now we'll learn how to maybe simulate a biased coin toss. Let's do that. So a biased coin toss. So the problem here is that using a fair coin, an unbiased coin, you want to simulate a biased coin. Right? This seems quite difficult actually. So given integers alpha m such that alpha is between 0 and m minus 1, simulate a coin toss with probability of heads being p, which is alpha by m. Okay, so that's the problem. So you know that unbiased coin automatically gives you half probability, but what if you don't want half, you want 1/3 or you want 10/11, right? So how do you achieve those probabilities using a fair coin? So simulate this using an unbiased coin. Right? Can this be done? So this actually looks difficult. Because how can you break this unbiased coin and make it crooked, right? Seems to really require you to change the material of the coin. But okay, of course, we'll give a mathematical solution for this. We'll not break the coin. So the idea is to sample x in 0 to m minus 1 and output heads if x is in the range 0 to alpha minus 1. Okay, so you have seen this algorithm how to sample an element in the range 0 to m minus 1. This solution is just one step ahead of that. So first you sample in the range 0 to m minus 1, and if x comes out to be actually in the sub range 0 to alpha minus 1, then you output head, otherwise you output tail. And you can see why this makes sense, because we intend to show that the probability of x falling in the 0 to alpha minus 1 window is alpha by m. Hence, this is like a biased coin toss. Right. So let's write down the algorithm. So x is a random number in 0 to m minus 1. This you can do by unbiased coin tosses, right? That will give you x in the range 0 to minus 1 uniformly distributed. And once you have this, you check whether x is less than alpha. If it is, then you have to output heads, else you output tails. right? So, since x is a random number in the range 0 to m minus 1 generated by using fair coin, you know that the chance of outputting head is alpha by m. So, that is it. So, number of random bits used is only log m, and the probability of getting head is the same probability as this random variable coming out to be in the range 0 to alpha minus 1, which is the size of interval 0 to alpha minus 1 divided by the size of 0 to m minus 1, which is alpha by m. Right, that finishes the implementation. So, that is about biased coin toss. And the final thing we will do is uniform sampling of permutation. Of elements 1 to n. This too you need in many applications when you like to have a random permutation, then you need this algorithm. Now, what is this to do with coin tosses, right? How do you get a random permutation? Notice that this is somehow similar to sampling k elements, right? There you are picking one element at a time and till you get k distinct elements. So, a similar idea you can use here. And since there are n factorial permutations, you want a permutation to appear with probability 1 over n factorial, right. So, that is what we have to analyze, but let us first see the algorithm. So, given n, you want to pick a permutation say as a string S. Okay, permutation we see as a string S. So, like 1 2 3 or 3 2 1, these are permutations of the set of 3 elements, or 2 1 3, right. So, see it as a string. The idea is as I just said, so keep picking an element x that is new. Okay, so random variable x, x1 will be something out of 1 to n, then x2 will be, you keep trying for x2 till you get something different from x1, and then x3 you keep trying till you get something different from x1 and x2 and so on. So, that obviously gives you a permutation in the end, but what is the chance, right? Is it uniform distribution? And use this to grow string S by x by appending x in the end. So, let us see the algorithm. So, S is just the empty string first initialized, so when we are looking for the ith element of the string, what we do is of course pick this random number. And if x is in S already, then this was a useless attempt. So, we have to retry. So, go to 2. Right, this seems to be an infinite loop. So, it may happen again and again that you keep picking an element which is already there in S, and so it goes on and on. But so obviously this is theoretically infinite, but practically you are expected to, after a while, get a new element and move forward. Then what will happen is you will grow the string S. Let us grow it by appending. In the end. Right. So, this way you get all the n elements and you output the string S. So, all that is left is to analyze what is the probability of getting a fixed permutation, our favorite permutation. What is the chance of getting that in this algorithm? So, as we did before, analyze the first 2 iterations. So, what you will get is for 2 different elements T1, T2, the probability that you get the string T1 followed by T2. This is that probability originally S was T1, then given that previous S is T1, you pick X to be T2. So, what is this? Picking S to be T1 is 1 by n probability, and based on that picking T2 will be 1 over n minus 1. And now you can induct on this. So, by induction on I, what you will get is probability that the string is this permutation, these elements T1 to Tn, distinct elements in some order. Probability of getting this is 1 over n factorial, right. You basically get n, then n minus 1, then n minus 2 and so on, which is 1 over n factorial. So, that is great. So, there are n factorial permutations, and getting any one of them is equally likely. So, that is the uniform distribution for you. What is the expected number of steps? Because remember, the algorithm is theoretically an infinite loop. So, we have to see, we have to analyze or give some guarantees on what happens in practice. So, let us, so all we can do is we can calculate the expectation. So, the expectation for the ith step, right, the infinite loop in the ith step, you are looking, it is looking for an x that is new, and I minus 1 have been already picked. So, this is like before, following expectation of a geometric distribution, and you get this 1 over probability. So, that is n minus I plus 1 over n, and take the reciprocal. So, which is n times 1 over n and finally 1 over 1. There is a harmonic series, so you get n log n. It is like integral of dx by x. So you get log of n. So you see that although theoretically it's an infinite loop, practically it is almost a linear time algorithm. So it's a very fast algorithm. Right? It's like its complexity is like sorting n elements, which we consider very fast. Okay, so that completes this sequence of algorithms which are very useful and very fundamental probabilistic algorithms that help you sample elements. And once you have seen them, you can come up with other kinds of sampling using these as a foundation. So in a similar spirit, we will now discuss an object that is extremely important in computer science and probably not studied in math courses. It is called hashing. Okay, this is used in almost all areas of computer science, but especially operating systems, databases, of course, theoretical computer science and cryptography. So basic question here is in computer science, there are many applications where a large set S needs to be mapped to a small set let us call it image set T. Okay, you want to map S to T, large to small, by a map phi. Why? Well, you can readily think of these examples like you have a list of very long website names. So instead of storing those long website names, you may want to shorten them, right? So you can, the simplest lookup table would be you just use the serial number. So first website number, second website, third. So you use 1, 2, 3, or you can come up with a more elaborate mechanism, because you don't want to always look at the lookup table. You want a function, you want a map, which should be easy to compute. Right. So instead of to avoid looking up in a lookup table, you actually want a function that is easy to compute, this function phi. So like shortening of long website names. So let's just say URL, and similarly mapping long addresses in the, let's say in the hard disk or in RAM, there are these long addresses, you want to shorten them in the virtual memory space. Or similarly, you have long file names, right? So labeling files. Or maybe in cryptography. So let's say encryption or signature. Right. So these are the few examples that come to mind where computer science needs hashing functions or hash functions. So we'll think of it always as a family of functions that we are after. So think of phi as a random function in a set phi r. Okay, so you have a family of functions, hopefully each of them is easy to compute, indexed by small r, which you should think of as a random string in the set or in the space big R. So denote random variable by phi big R. Okay, so that's the random variable which refers to some element of this set phi sub r. Okay, so now what do we want in hashing? So hashing from messages S to image T, or from domain S to range T, is called pairwise independent. We'll shorten it to PI. So we call it pairwise independent hash function or hashing family if random variables phi r s for S in the domain. So every element in the domain, when you look at its images under phi r, where r is this random variable, right? It depends on which string you pick, which hash function you pick. So phi r s is a random variable. This is a set of random variables. This is pairwise independent. And 2 is that for every S, you want phi r s. So as you change this small r, the image of small s will change, right? Different functions, maybe the image changes. The way it changes, that should be uniform. So phi r s is uniformly distributed. Okay, so you want phi r s to be pairwise independent and you want phi r s to be uniformly distributed, right? Then we call that it's a good hash function family, or it's a good hashing from domain S to range T. That these hash functions, when you look at some domain element S, the possibilities where it can go from using the hash functions, that is uniform. And when you look at S and S prime, two domain elements, then they are pairwise independent, no matter which phi r you pick. So some basic properties which are very important. I leave it as an exercise. This property 1 that we are saying, it basically means that for different S and S prime in the domain, and for all TT prime in the image, the probability that phi r s is T and phi r s prime is T prime. If you pick your two favorite domain elements and you randomly pick a hash function from this family, what is the chance that S goes to T and S prime goes to T prime? So, by pairwise independent, it should be uniform, right? So, which is 1 by T times 1 by T. So, square of that. Property 2, this says that essentially chance of S going to T is 1 by T. So, for all S in S and T in T, the probability that phi r s is T is 1 over size of T. Okay, so that is what you want from the random choices of the hash function phi from your family. You want this, and then you call it a good hashing, which is formally we are calling it PI hashing, pairwise independent hash function family. Just to give the intuition, so intuitively random phi r maps any subset A which has size not more than T. So, let us take this, okay, a subset of S, domain elements not more than the size of T, the range. If you look at the action of phi r on A, it is 1 to 1. In a 1 to 1 way. Okay, that is what is happening intuitively. This is a 1 to 1 action, but obviously there might be some bad phi r's, but if you do see this probabilistically, then most of the phi r's are good. They are actually for any subset A of size T, they are just changing the labels in a isomorphic way. Okay.